Hello there, and welcome to the Sleepy Science Society. Tonight, we drift into the quiet mystery of one of nature's most ethereal displays, a phenomenon that has painted the night sky with shimmering curtains of light since long before humans walked the earth. We're exploring why the northern lights shine, delving deep into the atmospheric science behind auroras, those ghostly ribbons of color that dance across polar skies in ways that seem almost alive. Imagine standing beneath a dark Arctic sky, far from the glow of cities, where the only sounds are your breath crystallizing in the cold air and perhaps the distant call of a raven. Suddenly, the darkness begins to shift. A faint, greenish glow appears on the horizon, barely visible at first, like dawn approaching from the wrong direction. Then it intensifies, spreading upward in vertical columns that ripple and fold like cosmic curtains swaying in an invisible breeze. Colors emerge, green giving way to pink, purple appearing at the edges, sometimes even deep crimson bleeding across the upper reaches of the display. The lights move with fluid grace, pulsing, brightening, fading, and reforming in patterns that feel both random and somehow intentional, as though the sky itself has become a living canvas. This is the Aurora Borealis, the Northern Lights, and it has captivated every culture that has witnessed it. Ancient Norse legend spoke of the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods. Indigenous peoples across the Arctic developed their own interpretations. Some saw the lights as spirits of the departed, dancing in celebration or warning. Others believed they were celestial beings playing games across the sky, or ancestral fires burning in the distant heavens. Medieval Europeans who witnessed auroras during particularly intense geomagnetic storms sometimes interpreted them as omens, as divine messages written in light, or as harbingers of war and plague. Even without understanding the science, humanity recognized something profound in these displays, something that spoke to the mysterious forces connecting Earth to the wider cosmos. But what we understand now, through decades of patient observation and elegant experiments, reveals something even more beautiful than mythology. The Northern Lights are the visible manifestation of a cosmic conversation, a continuous interaction between our sun and our planet's atmosphere and magnetic field. They are, in essence, the glow of energy being transferred across millions of miles of space, the luminescent signature of particles traveling at extraordinary speeds and colliding with the very air we breathe, but far above where any breath could reach. Understanding how this happens requires us to journey through multiple layers of science, from solar physics to magnetism, from atmospheric chemistry to quantum mechanics, all working together in a symphony that produces these ghostly lights. If you find yourself drawn to these quiet explorations where science becomes poetry and the universe reveals its hidden workings, I invite you to like this video, subscribe to the channel, or share your thoughts in the comments below. Your support helps more curious souls find their way here, one sleepy mind at a time. But for now, you need to do nothing except relax. Let your body settle. Allow your thoughts to drift gently as we begin our journey into the science of the aurora. Let's begin. The story of the Northern Lights begins 93 million miles away, at the surface of our closest star. The Sun is not the static, unchanging sphere it appears to be from Earth. It is a roiling cauldron of plasma, a state of matter so hot that electrons are stripped from atoms, creating a superheated gas of charged particles. Within the Sun's core, nuclear fusion converts hydrogen into helium, releasing tremendous amounts of energy that gradually work their way outward through successive layers. By the time this energy reaches the Sun's visible surface, the photosphere, temperatures hover around 10,000 degrees Fahrenheit, hot enough to vaporize any material we know of on Earth. But the story of auroras doesn't begin at the photosphere. It begins in the Sun's outer atmosphere, a region called the corona, which paradoxically is far hotter than the surface below it, reaching temperatures of several million degrees. Scientists still puzzle over exactly why the corona is so much hotter than the photosphere, but the consequences are clear. At these extreme temperatures, particles move with such violent energy that the Sun's gravity cannot hold them all. They escape into space, creating what we call the solar wind, a continuous outflow of charged particles, primarily electrons and protons, streaming away from the Sun in all directions. This solar wind rushes outward at speeds averaging around 1 million miles per hour, though it can move considerably faster during solar storms. Think about that velocity for a moment. If you could travel at the speed of the solar wind, you could circle the Earth's equator in less than 2 minutes. These particles carry with them a portion of the Sun's magnetic field, frozen into the flow of plasma in a phenomenon physicists call the frozen-in condition. As they travel, they create what is known as the interplanetary magnetic field, a vast magnetic structure that fills the solar system. The solar wind is not constant or uniform. It varies with the Sun's 11-year activity cycle, during which the number of sunspots and the frequency of solar storms waxes and wanes. During solar maximum, when the Sun is most active, its surface erupts more frequently with solar flares and coronal mass ejections. A solar flare is a sudden explosion of electromagnetic radiation, while a coronal mass ejection is something even more dramatic. 1 billion tons or more of plasma hurled into space at speeds that can exceed 5 million miles per hour. When one of these ejections happens to be aimed at Earth, it can take between 15 hours and 3 days to cross the distance between Sun and planet, depending on its initial speed. These coronal mass ejections don't travel alone. They bring with them their own magnetic fields, often much stronger than the background interplanetary magnetic field. As they barrel through space, they can sweep up and accelerate additional solar wind particles ahead of them, creating a shock wave in the plasma. When this surge of energized particles and tangled magnetic fields reaches Earth, it encounters something equally remarkable: our planet's magnetic shield. Earth is, in essence, a giant magnet. Deep within our planet's core, approximately 1,800 miles below the surface, lies a sphere of solid iron about the size of the Moon, surrounded by an outer core of liquid iron and nickel. The outer core is in constant motion, driven by heat escaping from the even deeper inner regions, and by the rotation of the Earth itself. This motion of electrically conductive liquid metal generates electric currents, and these currents in turn produce magnetic fields. Through a process called the geodynamo, these fields are amplified and then maintained, creating Earth's global magnetic field that extends far out into space. This magnetic field is not visible to our eyes, but it permeates the space around our planet, creating a protective bubble called the magnetosphere. The word literally means sphere of magnetism, though in reality, the magnetosphere is not spherical at all. Its shape is dramatically sculpted by the solar wind. On the side facing the sun, the day side, the solar wind compresses the magnetosphere, pushing it relatively close to Earth to about 6 to 10 times Earth's radius, or roughly 40,000 miles. On the night side, away from the sun, the solar wind stretches the magnetosphere into a long tail called the magnetotail, which can extend for hundreds of Earth radii downstream, millions of miles into space. Imagine the magnetosphere as a teardrop or a comet shape, with the rounded part facing the sun and a long, streaming tail pointing away. The boundary where the solar wind first encounters the magnetosphere is called the bow shock, named by analogy to the wave that forms at the bow of a ship moving through water. As the supersonic solar wind hits this boundary, it suddenly slows down and becomes turbulent, compressing and heating up. Just behind the bow shock lies another boundary called the magnetopause, which is the actual outer edge of the magnetosphere, where Earth's magnetic field effectively holds back the solar wind. But not perfectly. The magnetosphere is not an impenetrable fortress. Its strength varies depending on the orientation of the interplanetary magnetic field carried by the solar wind. Earth's magnetic field has a specific direction at any given location. Near Earth's surface in the northern hemisphere, field lines point roughly northward and downward into the ground. When the interplanetary magnetic field arrives with a southward orientation, opposite to Earth's field direction, something called magnetic reconnection can occur. Magnetic reconnection is one of the most important and dramatic processes in space physics. When magnetic field lines of opposite direction meet, they can break apart and reconnect in new configurations, like cutting and splicing together two pieces of differently colored string. During this process, magnetic energy is converted into kinetic energy, accelerating particles to high speeds. At the magnetopause, when reconnection happens, a portion of the solar wind can actually penetrate into the magnetosphere, injecting new plasma and energy into Earth's magnetic environment. Once inside, these particles don't simply fall straight down to Earth. The magnetic field guides their motion. Charged particles cannot move freely across magnetic field lines. Instead, they spiral around them, trapped by the magnetic force. As particles enter the magnetosphere, they find themselves caught in a complex magnetic geometry. Some drift eastward or westward, circling Earth. Others become trapped in regions called the Van Allen radiation belts, donut-shaped zones of energetic particles encircling the planet. Still others follow magnetic field lines that converge at the magnetic poles. Here's where the aurora begins to take shape. Earth's magnetic field lines loop through space, emerging from near the south magnetic pole, arcing out through the magnetosphere and returning to Earth near the north magnetic pole. Near the poles, these field lines converge and descend into the atmosphere. This geometry means that particles traveling along field lines in the magnetosphere are naturally guided toward the polar regions. As they follow these converging field lines, they accelerate, picking up speed as they approach Earth. The magnetotail, that long extension of the magnetosphere on the night side of Earth, plays a crucial role in powering the most dramatic auroras. Within the magnetotail, the magnetic field stretches and stores enormous amounts of energy, somewhat like a stretched rubber band. Periodically, this stored energy is released in a process called a substorm. During a substorm, magnetic reconnection occurs within the magnetotail itself, causing a sudden release of energy that accelerates particles earthward at tremendous velocities. These particles then stream along magnetic field lines toward the polar regions, carrying with them speeds approaching 1/10 the speed of light. Recent research confirmed in 2021 finally provided definitive proof of one of the key mechanisms accelerating these particles. Scientists demonstrated in laboratory experiments that Auroras waves, a type of electromagnetic wave that can propagate through magnetized plasma, play a central role. These waves, named after Swedish physicist Hannes Alfvén, who predicted their existence in the 1940s, are generated in various regions of the magnetosphere. As they propagate along magnetic field lines, they can interact with electrons, pushing and accelerating them in a process called resonant acceleration. The electrons surf along these waves like surfers riding ocean swells, gaining speed until they're traveling at enormous velocities, sometimes exceeding 20,000 miles per second, or roughly 45 million miles per hour. As these accelerated electrons approach Earth, they penetrate deep into the upper atmosphere, down to altitudes of around 60 to 300 miles above the surface. At these heights, we've left behind the dense lower atmosphere where weather occurs and where we live and breathe. We've entered the thermosphere, a region where the air is so thin it would be considered a vacuum by everyday standards. Yet even here, scattered atoms and molecules remain, and it's the collision between these atmospheric constituents and the incoming energetic electrons that creates the aurora. The thermosphere merges with another region called the ionosphere, defined not by temperature, but by the presence of ionized particles, atoms, and molecules that have lost or gained electrons and thus carry an electric charge. The ionosphere exists because solar ultraviolet and X-ray radiation constantly bombard the upper atmosphere, stripping electrons from atoms. But during auroral events, the ionization increases dramatically as energetic electrons from the magnetosphere add their impact to the sun's radiation. The air becomes a glowing plasma, though still far too thin to breathe, filled with excited atoms and molecules that are about to tell us their stories through light. Before we understand the colors of the aurora, we need to understand something fundamental about atoms and light itself. Every atom consists of a nucleus surrounded by electrons that occupy specific energy levels, often visualized as shells around the nucleus, though the reality is more complex. An electron typically occupies the lowest energy state available to it, called the ground state. But when an atom is struck by an energetic particle, or absorbs a photon of light, one of its electrons can be knocked into a higher energy level, an excited state. The atom doesn't stay excited for long. The electron soon falls back down to a lower energy level and when it does, it must release the energy difference. Often, this energy is released as a photon, a particle of light. The energy of the photon determines its wavelength, and wavelength determines the color of light we perceive. High-energy photons have short wavelengths and appear blue or violet. Lower-energy photons have longer wavelengths and appear red. Each element has a unique set of possible energy transitions, like a fingerprint. So each element emits light at characteristic wavelengths. This is how we identify elements in distant stars by analyzing their light. We look for these signature wavelengths in their spectra. In Earth's upper atmosphere, the two most abundant elements that contribute to auroras are oxygen and nitrogen. Above about 60 miles altitude, where auroras occur, oxygen exists predominantly as individual atoms rather than oxygen molecules. This atomic oxygen was created when molecular oxygen absorbed intense ultraviolet light from the sun, breaking the chemical bonds and splitting the molecules into individual atoms. When an energetic electron from the magnetosphere collides with an oxygen atom, it can kick one of the oxygen's electrons into an excited state. What happens next involves some subtle quantum mechanics. The most common visible auroral emission is a beautiful green color with a wavelength of 557.7 nanometers. This green light is produced when an oxygen atom relaxes from what physicists call the singlet S state to the singlet D state. The transition takes about 1 second on average, which seems fast, but in the world of atomic physics, it's actually remarkably slow. Why does it take so long? The answer involves quantum mechanical selection rules. Most atomic transitions happen via electric dipole radiation, an efficient process that allows excited atoms to release photons in a tiny fraction of a second. But some transitions are forbidden by quantum mechanical selection rules. They're not impossible, just highly improbable. These forbidden transitions can only occur through weaker mechanisms, and as a result, they take much longer. The green oxygen emission is one of these forbidden transitions. At lower altitudes where the atmosphere is denser, this slow transition becomes a problem. Before the excited oxygen atom has a chance to emit its green photon, it's likely to collide with another atom or molecule. That collision can transfer the excitation energy to the other particle instead, a process called collisional quenching. The oxygen atom never gets to emit its photon. The energy is lost to heat through collisions. But at higher altitudes where the air is thinner and the collisions are less frequent, excited oxygen atoms have enough time to emit their photons before being quenched. This is why the green aurora typically appears at altitudes between 60 and 150 miles. But oxygen has another trick. After emitting that green photon, the oxygen atom finds itself in yet another excited state, the singlet D state mentioned above. This state also cannot easily return to the ground state through normal transitions. The only way down is through another forbidden transition, one that's even more strongly forbidden than the first. This transition emits red light at a wavelength of 630 nanometers. Because this transition is so forbidden, it takes an extraordinarily long time, roughly 110 seconds on average. An oxygen atom in this state can sit patiently for nearly 2 minutes before finally releasing a red photon. 2 minutes provides ample opportunity for collisions to quench the excited state. At lower altitudes, virtually all excited oxygen atoms will be quenched before they can emit red light. Only at the highest auroral altitudes, typically above 150 miles and sometimes extending to heights of 300 miles or more, is the atmosphere thin enough for these patient oxygen atoms to finally release their red photons. This is why red auroras appear above green auroras when both are present. They're both coming from oxygen, but the red emission requires much higher, thinner air, where collisions are rare enough that atoms can take their time. The altitude difference also affects the intensity of red auroras. Because there's less total oxygen at higher altitudes, there are fewer atoms available to produce red light. Combined with the lower sensitivity of the human eye to red light compared to green, this means red auroras are typically much fainter than green auroras. They tend to appear only during the most intense auroral displays when particle precipitation is strong enough to excite oxygen atoms even at very high altitudes. When people report seeing brilliant red auroras stretching across the sky, it's usually a sign of an exceptionally powerful geomagnetic storm. Nitrogen, the other major atmospheric constituent, contributes different colors to the auroral palette. Molecular nitrogen is an extremely stable molecule. The two nitrogen atoms are bound together by a strong triple bond, and this stability means nitrogen atoms are relatively rare below altitudes of about 250 miles. Most nitrogen exists as intact molecules. When energetic electrons strike these nitrogen molecules, they can either ionize them, stripping away an electron to leave a positively charged molecular nitrogen ion, or they can excite the molecule without ionizing it. Excited neutral nitrogen molecules produce red and blue emissions. Nitrogen molecular ions produce blue and violet emissions, particularly a strong blue emission at a wavelength of 428 nanometers. These nitrogen emissions have a unique characteristic: they're prompt. Unlike the forbidden oxygen transitions that take a second or longer, nitrogen emissions happen almost immediately, within a millionth of a second or less after excitation. This means they can survive even at lower auroral altitudes where collisions are more frequent. The lowest edge of an auroral curtain, down around 60 to 80 miles altitude, where the atmosphere is relatively dense, often displays a purple or magenta color. This color comes from a mixture of prompt nitrogen emissions: blue from ionized nitrogen and red from neutral nitrogen molecules. Looking at an auroral curtain from below, you might see this purple lower edge, then above it the dominant green from oxygen, and if the aurora is particularly intense, red oxygen emissions topping the display at the highest altitudes. Sometimes observers report other colors as well. Yellow can appear as a mixture of red and green emissions occurring in the same line of sight. White light often indicates an aurora that is simply too faint for the human eye to distinguish colors. Our night vision relies on rod cells that are sensitive to dim light but cannot perceive color well. So, faint auroras appear colorless or pale white. Occasionally, a blue emission appears at the very top of auroral rays, caused by ionized nitrogen molecules that have been excited by sunlight. This sunlit aurora typically occurs near dawn or dusk, when the high atmosphere is still illuminated while the ground below is in darkness. The shapes that auroras take are as varied as their colors. The most stable and common form is the arc, a relatively uniform band of light that can stretch across hundreds of miles of sky. An arc might glow steadily for hours without much visible change, hanging like a luminous ribbon across the northern horizon. But auroras are rarely so calm. More often, they evolve into curtains or draperies, vertical structures that appear to hang from the sky like fabric, often with folds and ripples that give them a three-dimensional appearance. These curtains can move rapidly, folding and unfolding, brightening and dimming in complex patterns. When you're standing beneath an active aurora, the motion can be mesmerizing. Curtains sweep from east to west or west to east, sometimes both directions simultaneously as different parts of the display move independently. Bright regions pulse and spread along the curtains. Sometimes the bottom edge develops waves or scallops that ripple through the structure. The movements have been compared to flags waving in wind, though the wind here is not air, but rather the invisible push and pull of electrical currents and changing magnetic fields far above. From directly beneath an aurora, when magnetic field lines converge nearly overhead, you might witness a corona, where the rays appear to radiate from a point high above you, creating the impression of looking up into a tunnel or crown of light. This is purely a perspective effect, like looking up at parallel railroad tracks that seem to converge in the distance, but the effect is stunning, surrounding you with light that seems to converge on a celestial point. The structure of auroral forms is intimately connected to the structure of Earth's magnetic field and the electric currents flowing along it. Auroras tend to form in regions where field-aligned currents flow into or out of the ionosphere. These currents, called Birkeland currents after Norwegian physicist Christian Birkeland, who proposed their existence in the early 1900s, carry millions of amperes of electrical current along magnetic field lines. Where these currents flow into the ionosphere, electrons precipitate downward, creating bright auroral displays. The magnetotail's geometry drives much of the auroral dynamics. As magnetic field lines in the tail become increasingly stretched by the solar wind, they eventually snap back in a process of magnetic reconnection. This releases enormous amounts of stored energy, accelerating particles earthward and creating the substorms that drive the most dramatic auroral displays. The substorm signature in the aurora often begins with a sudden brightening of an arc, followed by an explosive poleward expansion as brightening and motion rapidly spread across the sky. These expansions can cover hundreds of miles in minutes, as energy stored in the magnetotail is suddenly released and funneled down magnetic field lines into the atmosphere. Auroras don't only occur in the northern hemisphere, of course. The southern lights, or Aurora australis, are equally spectacular, though far fewer people see them because most of the auroral zone in the southern hemisphere lies over the Southern Ocean and Antarctica, far from populated areas. The physics is identical. The same processes that create the aurora borealis in the Arctic create the aurora australis in Antarctica. In fact, because both auroral zones are connected by magnetic field lines that thread through the magnetosphere, auroras in the northern and southern hemispheres are magnetically conjugate, mirror images connected by the same magnetic field line. Observations from spacecraft have shown that auroral displays in conjugate locations can be remarkably similar, occurring simultaneously and showing similar structures. An observer in Alaska watching a particular auroral arc might have a counterpart in Antarctica watching the same magnetic field lines light up at the same moment. The symmetry is not the perfect. Differences in atmospheric composition, altitude, and the exact geometry of the magnetic field can create subtle differences between northern and southern displays. But the fundamental connection remains. The aurora is a planetary-scale phenomenon, painting both polar regions simultaneously. The auroral zones themselves are not fixed circles around the geographic poles. They center on the magnetic poles, which are offset from the geographic poles by about 11 degrees. The North Magnetic Pole currently wanders in the Canadian Arctic, several hundred miles from the North Geographic Pole, while the South Magnetic Pole drifts off the coast of Antarctica. The auroral zones form ovals centered roughly on these magnetic poles, typically lying between 60 and 70 degrees geomagnetic latitude. During quiet geomagnetic conditions, auroras stay confined to these high-latitude regions. But during geomagnetic storms, when coronal mass ejections deliver powerful blows to the magnetosphere, the auroral oval expands equatorward, bringing auroras to much lower latitudes. Historical records document spectacular auroras seen as far south as the tropics during extreme geomagnetic storms. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, produced auroras visible from Cuba and Hawaii. Telegraph systems around the world experienced massive disruptions. Operators reported sparks flying from their equipment, and some telegraph lines remained functional even after being disconnected from their batteries, powered by the electrical currents induced by the geomagnetic storm. The auroras that night were so bright that people in the Rocky Mountains reportedly woke at night thinking it was dawn. Such extreme events are rare, but moderate geomagnetic storms are fairly common, especially during solar maximum. The ability to forecast when auroras might be visible has become increasingly sophisticated. The key lies in monitoring the solar wind upstream of Earth. At a point called L1, about 1 million miles sunward of Earth, spacecraft continuously measure the speed, density, and magnetic field orientation of the approaching solar wind. When these spacecraft detect a strong solar wind with a southward magnetic field component, conditions are favorable for auroras. The data is transmitted back to Earth, giving forecasters 15 to 45 minutes of warning before the solar wind arrives. Space Weather Prediction Center, operated by the National Oceanic and Atmospheric Administration, provides real-time aurora forecasts based on this data. They issue alerts on a scale called the Planetary K-Index, or KP Index, which ranges from 0 to 9 and measures global geomagnetic activity. At KP values of 5 or higher, auroras become visible at lower latitudes, sometimes reaching as far south as the northern United States. At KP9, the highest level, auroras can appear as far south as the equator, though such events are extraordinarily rare. These forecasting capabilities allow aurora enthusiasts to plan viewing trips and give power grid operators warning of potential disruptions, as geomagnetic storms can induce currents in long-distance power transmission lines. The study of auroras has advanced remarkably in recent decades through a combination of ground-based observations, satellite measurements, and laboratory experiments. Scientists can now measure auroral particles and fields directly using spacecraft flying through auroral zones. The Polar spacecraft, launched in 1996, captured stunning ultraviolet images of the complete auroral oval, showing dayside and nightside auroral activity simultaneously. More recent missions like NASA's Themis constellation have revealed the dynamics of substorms in unprecedented detail, tracking the formation and release of energy in the magnetotail and its effects on auroral displays. One of the persistent questions in auroral physics was precisely how electrons gain their enormous speeds before striking the atmosphere. Various mechanisms were proposed, including electric fields aligned parallel to magnetic field lines and wave-particle interactions. The laboratory experiment published in 2021 finally demonstrated definitively that alpha waves could accelerate electrons to auroral energies through a process called Landau damping, where electrons moving at just the right velocity relative to the wave can extract energy from it. This confirmation resolved decades of theoretical work and observation, providing the missing piece in our understanding of how the magnetosphere produces auroras. Auroras are not unique to Earth. Any planet with a substantial atmosphere and magnetic field can produce auroral displays, and we've observed them throughout the solar system. Jupiter displays the most intense auroras in the solar system, powered by its immense magnetic field, which is 20,000 times stronger than Earth's. Jupiter's auroras are generated not only by the solar wind, but also by volcanic material from its moon Io, which is the most volcanically active body in the solar system. Io continuously spews sulfur and oxygen into space, creating a torus of plasma around Jupiter. As Jupiter's magnetic field sweeps through this torus, it accelerates particles that then crash into Jupiter's atmosphere, producing brilliant auroras. Saturn also displays beautiful auroras, particularly remarkable because Saturn's magnetic field is nearly aligned with its rotation axis, unlike Earth's tilted field. Uranus and Neptune, despite their great distance from the Sun and correspondingly weak solar wind, still show auroral activity. Even some planetary moons show auroral phenomena. Ganymede, Jupiter's largest moon, is the only moon in the solar system known to have its own magnetic field, and it produces small-scale auroras. Beyond planets, comets can produce auroras of a sort. When Comet 67P Churyumov-Gerasimenko was visited by the Rosetta spacecraft from 2014 to 2016, scientists observed far ultraviolet auroral emissions caused by the solar wind interacting with gases in the comet's coma. Even some brown dwarfs, failed stars too small to sustain hydrogen fusion, show auroral emissions, likely powered by interactions between their magnetic fields and their atmospheric circulation, or the influence of nearby companion objects. These extraterrestrial auroras teach us that the basic physics extends beyond Earth. Whenever charged particles, magnetic fields, and atmospheres interact, light can be produced through the same fundamental processes of excitation and photon emission. The details vary. The specific atoms involved differ. The energy sources vary, but the underlying principles remain consistent. By studying auroras throughout the solar system, we gain deeper insights into magnetospheric physics, atmospheric chemistry, and the behavior of plasmas in space environments. The scientific understanding of auroras emerged gradually over centuries. Ancient and medieval observers had only mythology and speculation to explain the lights. In the 17th century, scientists began systematic observations. The term aurora borealis was coined by Pierre Gassendi in 1621 after observing a particularly brilliant display visible across France. In the 18th century, observers noted correlations between auroral displays and disturbances of compass needles, hinting at a magnetic connection, though the mechanism remained mysterious. In the 19th century, understanding accelerated. Carrington's observation of the 1859 superstorm and its associated solar flare provided the first solid link between solar activity and auroral and magnetic storms on Earth. Scientists began mapping the auroral zones and noting their relationship to Earth's magnetic field. In the early 20th century, Christian Birkeland conducted pioneering experiments, creating miniature auroras in a laboratory by firing electron beams at magnetized spheres in a vacuum chamber. His experiments demonstrated that charged particles guided by magnetic fields could indeed produce luminous effects in gases, though many scientists of his era were skeptical of his ideas. The space age transformed auroral science. Rockets and satellites could measure particles and fields in situ, directly observing the processes that ground-based observers could only infer. The discovery of the Van Allen radiation belts in 1958 revealed that Earth's magnetic field trapped charged particles, and subsequent work showed how these particles could be energized and precipitated into the atmosphere. Spectroscopic observations identified the specific atomic transitions responsible for each auroral color. Modern computational models can now simulate the entire chain of processes from solar wind to auroral light, though many details remain subjects of active research. The recent confirmation of Alf-Venn wave acceleration in 2021 represents the latest chapter in this ongoing story of discovery. Scientists used the Large Plasma device at UCLA to recreate the interaction between alpha waves and electrons in a controlled laboratory setting. By carefully excluding other effects, they isolated the wave-particle interaction and measured definitively that electrons could be accelerated to auroral energies by this mechanism. The experiment vindicated Alf-Venn's insights from the 1940s and provided the proof that generations of space physicists had sought. Today, understanding auroras has practical importance beyond aesthetic appreciation. Geomagnetic storms that produce spectacular auroras can also disrupt modern technology. The same currents that power the lights can induce voltages in long-distance power transmission lines, potentially damaging transformers and causing blackouts. In March 1989, a geomagnetic storm caused a 9-hour blackout across Quebec, leaving 6 million people without electricity. Satellites in orbit experience increased drag during geomagnetic storms as the upper atmosphere heats and expands, and spacecraft electronics can be damaged by enhanced radiation. High-frequency radio communications and GPS signals can be disrupted by ionospheric disturbances. Space weather forecasting, with auroral monitoring as a key component, helps mitigate these risks. Despite our advancing knowledge, auroras retain their capacity for wonder. Modern understanding doesn't diminish their beauty. If anything, knowing the vast scales and complex processes involved enhances appreciation. When you watch an aurora dance across the sky, you are witnessing a story that began in the nuclear furnace of the sun's core, where energy was born in fusion reactions. That energy gradually worked its way outward over thousands of years, carried by radiation and convection through the solar interior. Eventually, reaching the corona, it heated the thin gas to millions of degrees and lent particles streaming outward on the solar wind. Those particles traveled for days across the void of space, carrying with them frozen-in magnetic fields. Upon reaching Earth, they encountered our planet's magnetic shield, itself generated by electric currents flowing in molten metal 1,500 miles beneath your feet. Some particles penetrated this shield, guided by magnetic reconnection at the magnetopause and accelerated by waves propagating through the magnetosphere. Following converging field lines to the polar regions, they plunged into the upper atmosphere at extraordinary speeds, each particle carrying energy across its journey. That energy was transferred through collisions to oxygen and nitrogen atoms and molecules, exciting electrons into higher energy states. And then, in those quiet moments when excited atoms released photons, quantum mechanics transformed particle energy into light that traveled in the final 100 miles to reach human eyes. All of this, the chain of causation spanning 93 million miles and multiple branches of physics, exists to paint the sky with color and motion, to create curtains of light that ripple and fold, to turn the night into a canvas where the invisible forces of the cosmos become briefly, beautifully visible. The northern lights connect us directly to the sun, offering tangible evidence that Earth does not orbit in isolation, but is continuously bathed in solar influence. They remind us that our planet possesses an active interior whose churning generates the protective field that shields us from the harshest space weather. They demonstrate that even the thin whisper of atmosphere at the edge of space contains enough atoms to transform energy into light. For those who witness them, auroras often create a profound sense of awe and smallness, a recognition of participating in something ancient and vast. Indigenous peoples who lived beneath auroral skies developed a relationship with the lights, incorporating them into stories and spiritual practices. Modern science offers a different kind of story, one told in the language of physics and chemistry, but the emotional impact remains. Whether you understand auroras through mythology or through Maxwell's equations, standing beneath them produces a similar response: wonder at the beauty and complexity of the natural world. As you settle into sleep tonight, perhaps you can imagine yourself standing on an Arctic plain, surrounded by silence and cold, watching the sky come alive with color. Green curtains unfold across the northern horizon, rippling and pulsing in complex patterns. A purple edge traces their lower boundary, faint but distinct. Above, if the display is strong enough, a wash of red spreads across the zenith, emitted by oxygen atoms 200 miles overhead taking their patient minute or two to release photons. The lights dance to rhythms set by events far away in the magnetotail, where stored magnetic energy releases in substorms. They glow with colors determined by quantum mechanical selection rules in oxygen and nitrogen atoms. They trace the invisible geometry of Earth's magnetic field. But none of these facts diminish the simple experience of watching them move, of seeing the sky itself become active and luminous, of witnessing light that has journeyed from the sun to the magnetosphere to the atmosphere to your eyes, completing a circuit millions of miles long in service of a moment of beauty. The aurora is science made visible. It is physics rendered in light. It is the cosmos putting on a show, and we are invited guests. If you found this exploration meaningful, I hope you'll consider liking this video and subscribing to the channel. Your support helps share these journeys through science with others seeking calm understanding in the quiet hours. Feel free to leave a comment sharing your thoughts or your own experiences with auroras. For now, let everything we've explored tonight settle into a soft background, like the quiet glow of the aurora on a distant horizon. You don't need to hold on to any of it. The knowledge is there if you want it, but right now, you can simply let go. Let your breathing slow. Let your muscles relax. Let your mind drift into the gentle dark, knowing that somewhere above, even if you cannot see them, the processes continue. The solar wind flows, the magnetosphere responds, and particles rain down along magnetic field lines to paint the polar skies with light. The aurora will still be there tomorrow, as it has been for billions of years, long before humans appeared to watch and wonder, and as it will continue long after. It is a permanent feature of our planet's relationship with the sun, a standing wave of light at the boundary between Earth and space. Rest now in this knowledge. Rest in the beauty of a universe that creates such displays, where the mundane interactions of particles and fields produce transcendent beauty, where the act of an electron changing energy levels can generate green light visible for hundreds of miles, where the same physics that powers stars also paints the night sky with color. Let your thoughts dissolve into this greater pattern, this cosmic conversation between our sun and our world. Sleep, well, knowing you are part of a planet protected by magnetic fields, graced with an atmosphere that can glow, orbiting a star that sends forth the wind that makes it all possible. Good night.